to our series of videos on linear algebra, where we begin with an introduction to linear systems. Now, linear systems are systems of the form, let's say x plus y plus a number, let's call it c, equals 0, or x maybe some multiplied by some constant ax plus by equals another constant c. All the values of the variables are just flat variables, if you like, raised to the power 1. So we do not have any x squareds and y squareds and xy's and any of such terms going on. All our terms are the simple x and y and so on. We could also have other variables like z, w, so you can have x plus y plus z plus w plus a plus b and so on going to 0. These can have coefficients and all of that. Now, we are familiar with linear systems in our previous studies. For instance, we can have a system of two simultaneous equations. Let's say x plus y equals 7, and then let's say x plus 2y equals 12. And we're familiar with how to solve such systems. We can use elimination and we can use substitution. So in this example, if we wanted to use elimination, we could subtract one equation from the other. So let's call this equation 1, call this equation 2. So we can subtract equation 1 from equation 2. So let's say 2 minus 1. What does that give us? That gives us y equals 5. And then we can substitute that value. So put y equals 5 in, let's say, equation 1. And what does that give you? That gives you x plus y, which is now 5, equals 7. That means that x equals 2. So by using elimination, we solve for x and y as we've done. And so this idea can be extended to more variables, where you now have some system of equations in the variables x, y, and z, and you want to solve for them to get the values of x, y, and z. So let's wipe our board and try to solve a system involving 3 unknowns. All right, so let's use the system. Let's say x plus y plus z equals 2, and then we have 3x plus 2y minus 5z equals 12, and then we have 4x minus y plus 3z equals minus 1. So these are now our 3 equations. We can call this equation 1, equation 2, and equation 3. And we want to use the same idea we used previously, that is elimination. We want to first eliminate x, and then later we're going to try to eliminate y, and then eventually we're going to get a solution for the system. So how do we eliminate x? Fortunately, the coefficient of x in equation 1 is 1. So we can just subtract a multiple of equation 1 from equation 2. And here, if we want to eliminate x, the multiple to use is 3. So if we subtract 3 times equation 1 from equation 2, so if we write, let's say, equation 2 minus 3 times equation 1, what does that give us? Well, that gives us, for equation 2, we're going to get x is going to go away, and we're going to have 2y minus 3y. That gives us minus y. and then we're going to have minus 5z minus 3z. So that's minus 8z, and that's going to be equal to 12 minus 3 times 2, which is 6. 12 minus 6, that's 6. So this is our new equation after we eliminate x from equation 2. Now we can call this equation 4. Let's also eliminate x from equation 3. So the coefficient of x in equation 3 is 4. So by subtracting 4 times equation 1 from equation 3, we're going to get rid of x. So let's say equation 3 minus 4 times equation 1. What does that give us? That gives us minus y minus 4y. That makes it minus 5y. And then we have 3z minus 4z. That's minus z. And then we have minus 1 minus 4 times 2, which is 8. So that's minus 9. And that's equation 5. So we've successfully eliminated x from equations 2 and 3. And now we have equations 4 and 5, which are just equations in y and z. So minus y minus 8z equals 6, and then minus 5 minus z equals minus 9. So here too, we can eliminate y from the second equation, and we can do that. One way to do that is to so we can multiply through equation 4 by minus 1, so we have a positive coefficient for y, or we can just choose to ignore and just multiply equation 4 by 5 and subtract it from equation 5. So whichever one we want to do is fine, but let's multiply equation 4 by minus 1. So we have equation 4 4 times minus 1, and that gives us y plus 8z equals minus 6. So let's call this equation 6. And then now we have this y plus 8z. We can multiply it by 5 and add it to equation 5. So let's multiply equation 6 by 5, and then we add it to equation 5. And what does that give us? Equation 6 times 5, we now have 5y. If we add it to the minus 5y in equation 5, the y disappears. And then we have 5 times 8, which is 40. So 40z, if we add it to the minus z, then we get 39z. Then we have 5 times minus 6, which is minus 30. If we add it to minus 9, we have minus 39. So minus 39. 39z equals minus 39. Now we could call this equation 7, but this equation is almost solved. We just have to divide both sides by 39 to get z equals minus 1. So that gives us a value for z, and we can substitute this value for z in the preceding equations. For instance, if we put z equals 1, let me write that down. If we put z equals 1 in, let's say equation 4, or maybe better to use equation 6, because we we multiply through by minus 1 to make it nicer. So put z equals 1 in equation 6, and what do we get? We get y. So let's say y plus 8z, so that's 8 times minus 1, and that's equal to 6. So we have, simplifying, we have y minus 8, sorry, we have y plus 8z equals minus 6, not 6. So here we have minus 6. And then we have y minus 8. Okay, that's equal to minus 6. So y equals minus 6 plus 8, which is 2. So we get a value for y. Now we can substitute the values for z and y into another preceding equation to get a value for x. So let's use equation 1, where we now say put z equals, okay, so here this should have been z equals minus 1. So even though I put the value minus 1 here I put 1, so that was an oversight. But we are putting z equals minus 1 and y equals 2. We are putting it in equation 1. And what does that give us? That gives us x plus y, which is 2, plus z, which is minus 1, is equal to 2. So we solve for x. We have x equals 2 minus 2 plus 1. So x equals 1. So we have that. By using the method of elimination, we've been able to get a value for x, a value for y, and a value for z. So this is a general principle that can be used to solve multiple systems or systems of multiple equations. And we can also try to get a geometric interpretation of what is going on. Now, if you recall that in the case where we have a system of equations in two unknowns, for instance, if you have, let's say, x plus y equals 1 and x minus y also equal to 1, what's going on is that if you sketch the line represented by x plus y equals 1, and you sketch the line for this one also, the lines are going to intersect. If the lines are not parallel, then they're going to intersect. And the point of intersection is the solution to the simultaneous system. And it is the same idea in 3 dimensions and even in higher dimensions. So if we have a system of equations in 3 unknowns, here, instead of each equation representing a line, it's representing a plane, or if it's more than 3, then a hyperplane. So you have 3 planes, and having one solution means that you have the 3 planes intersecting at one point. So if the 3 planes intersect at one point, that is when you have the unique solution, as in the case that we just did. But you can also imagine that the planes do not intersect in one point. In some cases, they will intersect in a line, and then in some cases too, they will intersect in a plane. So these are possibilities, and as you go into higher and higher dimensions, you can have different scenarios and different setups. And we're going to discuss all of them in the future lessons. Thank you.